All right, so I have slides. I'm going to talk, but I invite you to interrupt me at any moment and ask questions or make comments or exit me or something. Because I'm going to be talking about objective diagnostics, and Patrick already revealed quite a bit about it, so that's good because I can go quick in those parts. So we're all here to use observational data to generate evidence, and we're probably all convinced that that is a good thing to do. So we've been preaching to the choir, but actually not everybody in the world is convinced of the value of observational research. We've actually been doing some digging, and there are, we believe, three main reasons why we think that the reputation of observational research has been not so good. So we divided that into three buckets. So the first is probably the most obvious one. It's observational study bias. So we've talked already a little bit about confounding, and I'll go into a little bit on that later on. And we actually already talked a little bit about publication bias and p-hacking as well. And they're probably more relevant for observational research compared to randomized trials because, as Patrick already said, randomized trial takes a long time and a lot of investment, and an observational study far less. So just as an example of a voice outside of this room, so here's a paper by Roche and colleagues in the cardiovascular field where, well, the title already says what their opinion is of observational research. Association is not causation. Treatment effects cannot be estimated from observational data in heart failure. And I don't know if you ever had this when you submitted a paper and you got the review back and you had a nice observational study and you claimed to have found an effect, and then they said, no, you can't use the C word in your paper because it's an observational paper. You cannot say causes, you can only say is associated, which I think is pretty lame because we actually aim to establish, well, at least in the studies that aim to do that, to establish causality. So we should say that it causes if the data tells us that that's the case. So Roche tried to then explain exactly what is wrong with observational research. So in a randomized trial on the left-hand side, you have your drug, you have your outcome, and because you do randomization, there are no other confounding effects, and so you can directly estimate what that causal effect is. And if you do an observational study, well then you have all these confounders, and you know that you can adjust for them, but that even on the right, then afterwards you still might have your unmeasured confounders or other things that you did not adjust for because maybe you couldn't or you didn't know about it. And so, yeah, we know that it's bad, that people think it's bad, but how bad is it really? And so just to get a little bit of an insight into what our field is producing, in this plot here, what I did is I scraped PubMed. I pulled out all of the 200,000 something observational research papers that I could find. And I just extracted all the effect estimates that they mentioned, like their odds ratios or hazard ratios or incidence rate ratios. And I plotted those here. So there's a total of 111,000 estimates from those papers, and every blue dot is one of these estimates. On the x-axis is the effect size, so odds ratio, hazard ratio. And on the y-axis is the standard error. So that's basically how wide your confidence interval is. So the higher you go, the wider your confidence interval. And of course, like these are all sorts of studies on all different exposures, different outcomes, different designs. But regardless of that, I think you'll agree with me that there is a pattern quite clearly visible. And the pattern becomes even more obvious if I draw these two lines, which is the line where, of course, p-value equals 0.05. And anything below this is statistically significant. And you also notice that only 17% of the estimates have a confidence interval that includes one. So everything else rejects the null. That could be because people are just really good at picking hypotheses to test. which might be. We actually might wonder if it's worth actually then doing all the studies if there's already a 82% of probability of what you say is correct is correct. But another thing that's actually more damning in this plot is this very sharp cutoff at p equals 0.05. So there's no way you can statistically explain that except for the fact that people are doing publication bias and p-hacking. And well, publication bias, you're probably familiar with it. Like if you have a paper with a null finding, it's very hard actually to get it published. People are just not interested in it because it's not sexy. P-hacking, as Patrick already mentioned, actually that I've seen that happen a lot for the best intentions. If people have a hypothesis, I think this drug must cause this outcome, and then they run their study and they, well, p equals 0.06 or something, and oh, well, I'm sure I'm right. I must have done something wrong. And they just are a little bit more critical of the design when it's not reporting out what they think is true, and they just keep on improving the design until it actually shows what they think is right. But that, of course, invalidates their design, and that, both of those lead to a high rate of false positives. And so one of the more grander things that we've done in OHDSI is we've defined LEGEND, which stands for large-scale evidence generation in a network, and evaluation in a network of databases. And a core part of LEGEND is a set of principles that we define to tackle those exact three problems. So observational study bias, publication bias, and p-hacking. So these are the 10 guidelines. I'm not going to go through all 10 of them, but I'm going to highlight what I think are the most important ones and explain what they do. So the first one is LEGEND will generate evidence at large scale. So Patrick already said we can run these analyses not just for one exposure or one outcome, but we can run them for a large set of exposures and a large set of outcomes. For example, all drugs for an indication and then a large set of outcomes. And we will disseminate the evidence that comes out of this irrespective of what the effect size is. And of course, you can already figure out that those two should tackle publication bias, because you're going to look at everything and you're going to report everything. We will generate evidence using pre-specified analysis design and using a systematic approach. So it's not to say that we believe that you can do observational studies using a one-size-fits-all. It's just that we think that you might need to adjust your design for a specific question, but you can actually formulate rules that tell you how to change your design for different questions. And that in all makes it a systematic approach. And the idea, of course, is by pre-specifying this and not allowing you to change it afterwards, you should tackle p-hacking. And then the final two that I'd like to point out is we will generate evidence following best practices. I will tell you a little bit more about that. And we will use control questions. So that first one, best practice for addressing confounding. So our current best practice, as we define it, is large-scale propensity scores. You may have already seen it. It's actually the core of the cohort method package. So already the SOS study that you saw uses this approach because we want you to, because we think it's the best practice. So what does it do? It starts by defining a large set of generic covariates. So this is all conditions, all drugs, all procedures observed up until the point of your index date when you start one of the two treatments. So typically that's somewhere between 10,000 and 100,000 covariates that we construct from the data. We then use a regularized regression to fit the propensity model. We match or stratify on the propensity model. And interestingly, and I'm still amazed every time I see plots like this. So every dot on this plot is a covariate. So like I said, in this case, we had 58,000 covariates in this specific study. On the x-axis is the standardized difference of mean before matching, and on the y-axis, it's after matching. And so by using this approach, we were able to get every one of these covariates, every one of these 58,000, to have a standardized difference of mean below 0.1 after matching. And so basically balancing these populations in any way that we can see on the data. So anybody that has a discussion, yeah, but I have this confounder that you should adjust for, well, we adjusted for it. because we adjust it for everything that's in the data. So we wrote several papers on this approach. And the second thing that I mentioned is using control questions, which we use to measure residual systematic error. So control question is an exposure outcome pair where we know what the true effect size is, and most often what you'll see is we use negative controls, where we know that the exposure does not cause the outcome. And we basically use those in the same way that you use the same way that you would try to check if a scale is working properly. So we view our study design as an instrument that is measuring something, just like a scale. And a scale, you test if it works by putting something on it where you know what the weight is, and you see if the scale reports that exact weight. So that's what we do here as well. We apply the study design to those control questions, and we see whether we get the same results. And just as if your scale isn't quite right, there usually is like a button that you can, well, the old-fashioned one, you have to turn them. The new ones, you have to just push a button, but you can calibrate it. You can make sure that, no, this should be empty, 0 weight, so I calibrate it to now point to zeros. That's also what we can do with these negative controls. We can apply empirical calibration to our p-values, our confidence intervals, and other statistics that we reproduce. And again, several papers on this topic. So an example of one such LEGEND study that we've completed a couple of years back is the LEGEND hypertension study. So you don't have to see the whole diagram, but basically the idea is here we compared all first-line hypertension treatments, both monotherapy and dual therapy, which you see here leads up to 12 or almost 13,000 comparisons of drugs. We included 55 outcomes of interest, so that leads to almost 700,000 research questions of target versus comparator for an outcome. We included negative control outcomes, 76. We actually included some positive control simulated outcomes as well. Confounder adjustment using the large-scale propensity score, so that's a lot of propensity models, 13,000 of them, and across a network of 9 databases. So this is what came out of that. So again, the same type of plot I was showing before. Every dot here is a hazard ratio that we produce from one of these databases for one of these 700,000 questions. And of course, the main point I'm trying to make here is that this distribution looks very different from the one that we saw in literature. And even if you were to limit that distribution from literature to just those papers on hypertension treatments, it's very, very different. And the main point, of course, is, yeah, it seems like at least we've tackled here the publication bias and the p-hacking problem. And we would assert also the observational study bias, at least to a large extent. So from that, we were able to publish a slew of high-impact hypertension papers published in literature. But the thing I wanted to now switch over to is the idea of diagnostics, because we didn't just produce 7 million hazard ratios. Each one of those hazard ratios came with diagnostics. And we provided those as part of the evidence base. So we have a Shiny app, a LEGEND hypertension Shiny app, where you can go to, and you can click on like the comparison, and it will report out hazard ratios across databases, but also give you all these diagnostics, such as statistical power, covariate balance, and systematic error as observed with these negative controls. But we just provided them as is, leaving it up to the consumer of the evidence to now interpret these results. So for example, in those papers that I showed you, we as authors of those papers had to look at the diagnostics and decide whether we were satisfied with them enough to actually show them to the public. And so the question that I want to go into for the rest of my talk is, well, can we use these in a more systematic way, these diagnostics? So Patrick already showed this plot, so it can be brief, but the idea is that you have 3 levels of diagnostics. You have your database diagnostics, your cohort diagnostics, but I want to focus on that third part, the study diagnostics. We have diagnostics defined for all of these, but these I find the most interesting ones for me anyway. Yeah, skipping this. So, so for the next part, this is going to be the more practical part. I want to tell you what the exact diagnostics are that we currently have for study diagnostics. And I already heard a good one that we don't have, which is the proportionality assumption that goes into the hazard ratio. We don't have that yet, but we agree that we should. So it's not yet in there. So the first one is statistical power. And there actually has been quite some discussion on statistical power in observational studies because it's fixed. In a trial, you do your power calculations to determine how many people you should enroll in your trial to measure a certain effect. But we just have data, and whether or not that is enough power to detect a certain effect is a given. You can't change that. So what we do is instead of computing power, we basically invert that and we compute, given the power that there is, what is the minimum detectable relative risk. So yeah, given how much data you have, could you, for example, detect a relative risk of 2 or 3? And another discussion that's been going on is, well, do you actually need to not do a study when you don't have enough power? Because even if you don't have enough power, you'd still have maybe a point estimate with a wide confidence interval, but it would still tell you at least something. And so there's this paper by Miguel Hernan, which actually argues where we don't care about power calculations at all. And to a certain extent, I agree with him, because as long as we're generating evidence and we're being clear about the uncertainty in the evidence, then I think that's a good thing. But I think there is a limit. So for example, like the bottom one in this forest plot, it has a tight confidence interval. That's very convincing. The top one, I've seen so many people when they see an estimate like that, they draw the wrong conclusions. They start to panic. Oh my God, it's a hazard ratio of 4. But no, it's we actually don't know what the effect size is. It's such a wide confidence interval. And so that's why we have this rule which set a very high bar. Oh, actually it's a low bar, but the number is high. You should have a minimum detectable relative risk of 10 or smaller. So if you can't even detect a relative risk of 10, and we'd never look at effect sizes of 10, then maybe we should just not report it out, because then you have these really wide confidence intervals that people don't know how to interpret. Next up is equipoise. So in a randomized trial, of course, you know the probability of getting one treatment over the other is usually 50% because it's an equally matched trial. And that allows for exchangeability. But in an observational study, there could be reasons why one group gets one treatment and the other group the other. And we actually are able to measure this because we compute a propensity score. And that tells us how different those two groups are. And so we actually have Alec Walker proposed this criteria, which I think is a very nice one, this metric. It's called the equipoise. So the preference score is a direct transformation of the propensity score. It doesn't really matter that much. And then you simply count what percentage of your population is within certain bounds between 0.3 and 0.7. And so on the left-hand side, you see the propensity score distributions overlap very nicely. So the two groups are very comparable. So that has an equipoise of 83%. So they're comparable. On the right-hand side, they're very separated. So there are only very few people that had one treatment but could have gotten the other treatment. Most people actually, you already knew beforehand they would get one treatment and they were not very likely to get the other treatment. So in that case, the equipoise is low. There are not that many people in the middle. And so we've defined a threshold, or actually that we follow the one from the Alec Walker paper, which says that equipoise needs to be greater than 0.5. And we currently don't have that actually hard-coded in Strategist because it's a very strict one, as you'll see later on. But I'm going to show you some evidence like what that would do if we impose that. And so the reasoning is, well, if equipoise is low, then the populations are very dissimilar. And so we probably are not going to be able to make them similar enough to actually do proper causal inference. Bless you. All right, the next up, this is the more well-known one, I think, covariate balance. So the idea is, well, we have an exposure and outcome, and then we have confounders that are associated with both of them. And we want to make sure that we at least break the arrow between confounder and exposure by making sure that the two exposure groups have basically the same prevalence of the confounder. And so, of course, if you do adjustments like propensity score matching, one of the goals is to make them more similar and basically introduce balance so that the prevalence of all the covariates is the same in the two groups. And we can measure that, of course, using the standardized difference of mean. I already showed you a plot like this. And our rule has been always and still is that no covariate may have a standardized difference of mean greater than 0.1. Why is 0.1? Well, Peter Austin once said 0.1 might be a good idea, and as it always happens, if somebody says something like that, then all of a sudden this becomes a law, even though that was never his intention. And if you ever actually go back and read why he said that, he just referred to some very standard statistical textbook. But yeah, there's no hard reason or rhyme behind that. But still, we currently use it as our threshold. Next up, generalizability. Nice thing about real-world evidence is that in theory it tends to be more generalizable than a randomized trial. So we take everybody in the observed population, but then we do things like propensity score matching, and all of a sudden we're no longer looking at the same population that we're starting with. And so generalizability is the extent to which the analytic population that we ended up actually fitting the model on, how does that differ from the population that we originally started with in the data. And so we follow this paper by Elizabeth Tipton, who proposed a diagnostic for this, which is very similar as to the previous one. So it's the standardized difference of mean for covariates, but now not between the target and comparator, but between the target as you pulled it from the database to the target cohort as you ended up after propensity score matching and all other adjustments. And so it's testing whether those are very different. And we use a slightly different cutoff here, 0.25, just because those differences actually tend to be somewhat bigger. And so the reasoning here is if the standardized difference of mean is greater than 0.25 for any of the covariates, we might not generalize to our target population. And again, this metric or this exact diagnostic currently isn't implemented in Strategist because it's also pretty strict. But I'm going to tell you about an evaluation that we did. And we're thinking about using this as a formal diagnostic. The last one is residual systematic error. So of course we do our fancy propensity scores, or we may do some other adjustment to produce confounding. But we might still make mistakes or have the model misspecified. And that's what we use our negative controls for. So we measure whether after all of these fancy design choices, our study design is able to produce the results that we thought should be the correct answer. And so we can look at the distribution of these negative controls and see whether or not they are in line with what we expect. And so this is another diagnostics that basically measured how well you're doing after all of your adjustments. And to explain a little bit about how we measure that, so here at the top, you see every black dot there is a negative control. Again, x-axis is the effect size, hazard ratio, for example. Y-axis is standard error. And I'm showing you two different designs, actually, in this case, that were applied on the same data. And well, you can already see what the negative controls are telling you here, right? On the right-hand side, the negative controls are nicely centered in the middle. And of course, as standard error goes up, they they can drift a little bit further away because their confidence intervals are wider. There's more uncertainty there. And on the left-hand side, you see, well, there's something funky going on there. They're all shifted to the right. So this method appears to be positively biased, which was also our conclusion. So that's all nice to look at, but of course we want to quantify that. So one thing that the first step that we take is we fit a model to that. Just a normal distribution is fitted to these negative controls, taking into account the uncertainty as expressed by the confidence interval. And so I'm showing you below the fitted distributions, and this is basically telling you exactly, but now in numbers, what you saw in the upper plots. So below you see that the mean of this distribution is shifted all the way to the right, 0.48 on the log scale, so that's actually quite far. So the expected value here is actually, you're almost expected to get a relative risk of, well, 1.8, even if the null is true. And on the right-hand side, you see that that method, the self-controlled K-series design, is very unbiased, having a mean of almost 0 and a standard deviation of almost 0. And so having it in two numbers, mean and standard deviation, is actually still a little bit annoying if you want to use it as a single metric with a single cutoff. So we summarize that into what we call the E-score, the expected absolute systematic error. So that's just, you take the absolute value of that normal distribution, and then you take the expected value of the absolute value, and that is your E-score. Might sound a little bit complicated, but basically the idea is that if your E-score is 0, that means that for the negative controls, all of the distribution that you see in point estimates is completely explained by the random error. So the only error that appears to be there is random error, meaning there's no systematic error, which means you have an unbiased estimator, at least for these negative controls. So we sort of, I mean, we've done this a lot of times, so we now made up a rule, just like Peter Austin once did, that the E-score shall be no greater than 0.25. And if it is, then we might be able to actually still get a correct estimate by using calibration, but we're just not going to trust it anymore. We just like garbage in, garbage out. If your method is that noisy, then we should just stop at this point and maybe go back to the drawing board and see how we can get a better design. So as the discussion was earlier, like that is totally fair game. Because if you're looking at your negative controls, you haven't yet looked at your outcome of interest. It's totally fair game to now go back and see how you can get a better distribution for your negative controls. All right, so wrapping this up, these diagnostics can provide evidence that your study is doing the right thing. But, well, as I mentioned, there are also like pretty arbitrary choices there, right? And just, they sound like a good idea, but are they actually? So some work that we did last year, I think, was, well, can we actually measure how well they work? So this, for me, is the fun part. So we went back to this legend hypertension study. And we thought, well, how can we evaluate in this study how well these diagnostics are? And we realized we need another gold standard. So we already specified a set of negative controls, 72 negative controls in legend hypertension, but we actually need a new set. And so we went about just creating a completely new set of negative controls, which is slightly different from the previous set. We went to the product labels of all of these hypertension treatments. And, well, as you know, these labels tend to be very inclusive. If there's just a suspicion of an outcome, it will be included. So we required our negative controls to not be mentioned on the label. But it's only when you compare two drugs. So you have two drugs, and neither of the drug has an outcome, an adverse event on the label. And actually, we go back up one level. If none of the other drugs in the same classes also don't have the adverse event on the label, then we believe it to be a negative control. So just as an example, so ACE inhibitors, like lisinopril, well, it's fairly well known that those might cause angioedema. So that's certainly not a negative control for ACE inhibitors. Calcium channel blockers and ARBs probably don't have this side effect, but as I said, these labels tend to be very inclusive, so they still listed on post-marketing experience, which means that at least one patient experienced that when taking one of these drugs. But if you look at the direct vasodilators and the alpha-1 blockers, they don't have angioedema anywhere on the label. And so in this case, we'll just posit that, for example, hydrolazine and prazosin, I'm so bad at drug names, sorry, prazosin, that those are probably for angioedema are a negative control. I mean, it might not be true. It actually is true, we'll see later, but might not be true, but at least now we know that that's probably true, and that can serve as a way to measure if our diagnostics are actually having an effect. I'm going to skip over this next example. So now we've created a new set of negative controls, and actually we have almost 10,000 target comparator outcome triplets where it's likely that the null is true. It's actually symmetrical, so it's 2 times 4,800, which form a new set of maybe imperfect negative controls. Imperfect in the sense that the null might still be true. The difference between the negative controls used in Legend is that in Legend, these 72 negative controls, they were only to be used within a target comparator outcome comparison. Here we're using them across all analysis. Also, in Legend, the original set of negative controls, we excluded anything that was known to be associated with any hypertension treatments. They're actually a more strict criteria. Yeah. If we just run we use our Legend hypertension results right now on this new set of negative controls, we actually get an E-score of 0.38, which is actually crossing our previous set boundary of not being good enough. But that is before applying any of the diagnostics. So certainly if you don't apply diagnostics, then we wouldn't trust what came out of Legend hypertension. But of course we did. So, all right, so I'm going to skip right ahead to the results just because we don't have that much time. So what we did is for all the 5 diagnostics that I mentioned before, with their proposed cutoff, we measured how many of the estimates in Legend hypertension actually failed the diagnostic. And here we focus just on the monotherapy comparisons, just because else it's a very full set, but that doesn't really matter. So power, as I said, it's a very low bar, high number. So only 5% of things failed this threshold because, yeah, you usually have more than enough power to at least detect them at a relative risk of 10. The opposite end of the spectrum is equipoise, requiring that to be greater than 0.5. Well, that now eliminates 71% of your studies, basically. So that's very drastic. Covariate balance, like I said, it's our standard rule, which we actually do apply everywhere. That gets you, eliminates 56% of your studies. What it does to our metric of basically how much bias is remaining is also very different. So of course our power metric, well, it does absolutely nothing because it also eliminates almost nothing. Requiring the equipoise greater than 0.5, which is the most restrictive one, does have a big impact on the remaining systematic error. So our E-score goes down to 0.02. Covariate balance has some effect, the diagnostic, but not as much as I was expecting. So we end up with 0.28. That's true. Generalizability, again, doesn't have a big effect, but I think both power and generalizability are actually in a bit of a category on their own. They don't actually, those 2 diagnostics don't aim to improve your systematic error. They aim to improve something else. They aim to improve your interpretability of the results. So that's maybe not so surprising why they don't have a big effect on the E-score. Also, that's measuring all of them on their own. If you combine all of them, well, then your E-score becomes 0. So you have a completely unbiased estimator, but you lost 88% of your study estimates. So that is definitely showing that applying these diagnostics seems to have a big effect in terms of improving the reliability of your results. So you should not ignore your diagnostics is the main message I would like to make. But it also tells you if you strictly follow all of these rules, which I already mentioned, we currently don't do in strategies, you lose 88% of your study results, which might be a very big price to pay. So just as a more of a thought experiment, we thought, well, can we do better? These thresholds currently are basically just made up. What if we just treat this as an optimization problem? So we have an objective that we want to achieve. We want to maximize the number of studies that don't get kicked out while having a small E-score. So let's just try and see how we can do that the best. And just run the optimization. And so on the right-hand side, I'm now showing you the optimized set of rules. So for power, generalizability, and systematic error, you should actually not have thresholds. We can throw those away. Equipoise should be greater than 0.5, and covariate balance, the standardized difference of mean, can be no greater than 0.5, which is a sharp deviation from Peter Austin's 0.1. If you only apply those two diagnostics with those thresholds, then instead of 88% failing, you have 71% failing. So that's a rather big increase in the number of estimates remaining, and your E only goes up to 0.02. So when we first gave this talk, people thought I was now saying this is the new threshold to use. I'm not saying that. I'm just saying that this is an interesting thought experiment, and we need to do some more research in like what are really the set of diagnostics that we need in OHDSI. So wrapping this up. Yep, sure.
A big point that I want everybody to understand is a majority of your studies are going to fail diagnostics. And we have to come to terms with that because very few people like the idea that they're going to spend all the time to do a study and then be told they got nothing at the end of it. So this is explicitly saying if you do studies and you want to follow good practice and good rules, you should expect that a majority of the time you're going to end with no results. And that's a tough pill to swallow. But it's a necessary pill. It's the reason why there's so much crap in the literature, because everybody publishes whatever they want. But if we're going to get to the point where we have reliable evidence, it has to mean that we're willing to stop a majority of the time.
Yeah, so when we do these type of studies, for example, within J&J, where we work for, we very explicitly use these top rules to say, okay, I'm sorry, you have this question, but the data can't answer your question, so we're not going to give it to you. And I do think that is the right thing to do, but as Patrick said, like for us, it's easy because we invested all this time and we got paid to do it nevertheless. But if you're an academic and you're doing the study in the hope of getting a cool paper, then realizing that you might need to stop might be a difficult decision. All right, so the evidence that we generated here in this small experiment, well, it's actually a pretty big experiment, is that these study diagnostics actually can help improve the reliability of the evidence. Some of these diagnostics actually might have different goals, such as the power and the generalizability, which aim to improve not reliability, but more the interpretability and generalizability. Up to now, these diagnostics rules were arbitrary, and we have some first evidence that we might actually come up with better thresholds. But I do think we need more research. I don't know how much this will generalize to fields outside of hypertension. All right, so what is our strong advice for you? So we don't want you to post hoc look at diagnostics, because that could lead to p-hacking. Like Patrick already said, yeah, oh, the hazard ratio is exactly what I thought it would be, so I don't actually care about whether the proportionality assumption held. So they should be pre-specified, for example, in the protocol. So here's an example from a recent protocol from one of the OHDSI collaborators, where they very explicitly in the protocol say, these are the diagnostics that we will apply, and these are the thresholds, and we will not look at anything that fails these. So basically, there are two ways in which you can use this knowledge about diagnostics. So one that we've mostly applied in the past is that you actually have the results of the diagnostics inside of your protocol. So you start with your research question, you write your protocol, and simultaneously you already basically start implementing your study by selecting cohorts and everything. And then you execute up to the point where you have diagnostics, and then you might realize, oh, now my negative controls are showing too much systematic error, or my covariates are out of balance. And it's totally fine at that point to revisit your protocol and reiterate up to the point where you meet all your diagnostics, and then the best practice would be to then include the diagnostics in your protocol, saying this is what we're going to do to get the answer, and this is why we know that it will be a reliable answer. So once that's done and you pass diagnostic, well, then you first you register your protocol, maybe the actual code of your study package. You run the last bit of the study, which is just a very small bit at the end, and you get your results. Yep, go ahead.
So what you're suggesting is that you define a protocol and write your protocol, which includes the analytics that you're going to do. Meanwhile, you're doing your cohorts, generating your cohorts, and running the diagnostics on the cohort. But none of the diagnostics rely on the actual execution of the analytics. Is that what you're saying?
No, actually, they do. Like,
so how do you keep them blind?
Also, so strategist automatically keeps them blinded. So that's implemented.
Somebody can see them, so you have to have something in place so that.
Yeah, also, so the Shiny app won't show them. So, but in the end, there's always a bit of trust that that's the only solution there. One thing that you said that also triggered me. The usual process that we follow is not write a protocol and then implement, for example, the cohorts. We actually tend to do it the other way around. We go to Atlas, define the cohorts in agreement with everybody involved in the study. And then once you're done, there's a nice button in Atlas that says print friendly. And then you have a very nice, almost human readable description of the cohort that you can put in the protocol. So that's, yeah, putting the horse in front of the cart or the other way around. So that's one way to do it. The other way that we are now following more in strategies is instead of having the full diagnostics be in your protocol, you actually, just like in the paper I showed you before, you pre-specify what your thresholds are, and then whatever comes out of your analysis, you decide then based on the pre-specified thresholds whether or not you're going to unblind it. So I think we're sort of on a path here in OHDSI where we here have the process of a study, which is define research question, generate evidence, then interpret whether or not you think your study will be reliable, and finally actually interpret the study results. Where in Legend Hypertension, we started taking the first two steps, making those more pre-specified. So normally, of course, like all of these would be much more ad hoc, but in Legend, we set up a systematic process for defining all of the research questions. We just said, we're going to look at all hypertension treatments. So that became systematic, and then also the way in which you generate the evidence became fully systematic. So we had a process that we applied, and we didn't deviate from that after viewing the results. And the new thing that we're proposing here, which is being implemented into strategies, is that also that third step of interpreting the reliability of the study itself becomes more systematic by pre-specifying the thresholds. So yeah, the key word being pre-specified. Yeah. And with that, I've still got 3 minutes left. All right, thank you. Any questions? We have 3 whole minutes. Yep, go ahead.
this is something that probably is debatable, but just to maybe give some hope after Patrick's comment that where you started in the beginning when you were speaking about p-hacking and publication bias is, well, maybe researchers do have accurate hypotheses about what will and won't be an effect. And I think if you start with a good hypothesis, probably the kind of 88% that actually don't pass diagnostics will be slightly less. So
No, that's actually,
just for everyone, don't lose heart.
Point. So
Yeah.
in Legend Hypertension, we did all hypertension treatments and we compared all of them, even the ones where you could beforehand already have said, no, that's a dumb idea, you shouldn't do that. So in truth, of course, yes, you're right. We will have more studies pass all diagnostics. Yes, thank you.
It requires courage to stop. And I think that there's... So it does require courage to stop. And there's two aspects of that courage that I think we need to think about as a community. One is, if you learn that you can't answer a question appropriately, that's probably a publishable unit. And you should actually take the energy to write the paper to say, we wanted to answer this question and we couldn't for the following reasons. The courage that takes there is to write something that you know that journal editors are going to find very unsexy. And so you're probably not going to get that paper in JAMA. The second courage is to actually have the commitment to stop because you think you've got unreliable evidence. And Martijn mentioned, like, when we're wearing our day job hats, we have had numerous occasions where we've said we are stopping, and we've been pummeled by questions of, come on, you're right there, you've got the answer, can't you just give it to us? And so you have to have the courage to say, no, you come to us because we will generate reliable evidence. And part of being reliable is saying when it's not reliable. And these are rules that declare it's not reliable, so you've got to honor them. But that definitely takes courage, and that is not the current paradigm of observational research in the field at large.
Yeah, and I know we're not actually selling this very well, but it can be very frustrating if you've done a study, you fail diagnostic and you stop, and then you see in the literature somebody else who did the study and did not perform any diagnostics and now is reporting the result that you had that you know is not reliable. But yeah, I don't think, I think if we want to move forward as a field and get out of this, like, we all believe observational research is good, but there is a large chunk of people out there who are not at all convinced of that. So if we want to actually get a better reputation, we have to be better at generating reliable evidence.